Hello everyone, I'm Lucas from Crystal Tech Company. Today, I will introduce crystallization, characteristics of high-purity compounds, and the development direction of crystallization process technology. High-purity compounds have extremely strict requirements for purity, and crystallization is the final purification step. The market price for these products has consistently been high. In the past, the production process involved chemical synthesis followed by crystallization for separation and purification. If the purity fell short after the first crystallization, a second or even third recrystallization was needed to improve it. Once the standards were met, the product was ready for delivery. Now, the fine chemical industry faces intense competition. Companies are focusing on reducing cost and improving efficiency. However, the crystallization step is often inefficient and has significant room for improvement. Multiple recrystallizations to a single step, while still meeting high purity requirements, can greatly cut costs and boost efficiency. The key to achieving this is identifying the source of impurities and understanding the root cause of why crystallization fails. To remove them effectively, impurities including trace impurities, residual solvents, exist in several forms, adhering to the crystal surface, embedded within the crystal lattice, or entrapped within crystal aggregates, or polymeric structures. Among these, impurities embedded inside the crystals, or entrapped within aggregates, polymer-like structures, cannot be removed by conventional methods and typically require recrystallization. So the most challenging impurities to address, necessitating targeted optimization of the recrystallization process. The root cause of impurity entrapment can be attributed to improper control of the crystallization process. Crystallization is inherently a process of impurity exclusion. If properly controlled, it can theoretically produce regular, large, high-purity crystals, while avoiding impurity incorporation. However, uneven crystal growth and a high proportion of fine particles tend to promote the formation of aggregates that can trap impurities or residual solvents, leading to impurity entrapment. To address these two types of impurity challenges, the core solution lies in precise control of the crystal nucleation and growth processes, aiming to cultivate uniform, large and well-structured crystals. This approach can minimize the need for multiple rounds of recrystallization, potentially achieving high purity requirements in a single crystallization step, significantly reducing production costs in the crystallization state. Thank you for listening.